All right, so I'm mostly going to start off by just recapping what we did at the end of last time. And then I will start a little bit on non-interacting bosons. We've only got 10 minutes, so I may not even get through the recap from last time. But it's important, so I'm going to go through it carefully. So what we did last time was I showed you the most important thing that you've learned up to now is why the grand canonical distribution is a good thing. So let me just recap what we talked about. So what we talked about was this. If you look on the right-hand panel, we look at what happens if you just use the Boltzmann distribution, which everybody normally prefers. So you've got the partition function for n particles, and we've written it down as e to the minus beta times the energy. And then you sum over the states, and the states in this case are the single particle quantum states. So we sum over their quantum numbers, which are their occupation numbers. And the particles are fermions, and so the occupation numbers up to spin are just 0 and 1. So if you think of the states as being represented by the states, and then individual states with different, which are the same except for spin, are counted as individual states, then we just sum over the occupation numbers 0 to 1. And that first line is just the partition function, but it has this n in it. It has the number of particles in the system. And so that constraint then means that the sum of the occupation numbers has to add up to n. And that is the thing that is a problem. And why is it a problem? Well, if I write down what the energy is just the sum of the occupation numbers of the states times the energy of the states. And the particles are non-interacting, so the energy of the states just depends on the state itself. It doesn't depend on what the other particles are doing, so there's no interactions there. And so the sum over states, when put into the factor e to the minus beta e, that then factorizes because e to the a plus b, if a and b commute, is the same as e to the minus a times e to the minus b. And so then this thing factorizes, and the problem is that this part over here, this part, that factorizes as well, but the constraint does not factorize. And so it's hard to evaluate the partition function. So the problem that is solved then by the grand canonical distribution is listed over here. What happens is that when I write down the partition function, it has a constraint that does not factorize. And the trick about the grand canonical distribution is shown on the bottom of the page, namely that by summing over the number of particles, total number of particles from 0 to n, the constraint goes away. We have a sum of over the states of whatever function it is that we're summing, but those sums are subject to the constraints that n equals 0, n equals 1, n equals 2, all the way up to n equals infinity. In other words, therefore, there is no constraint. In fact, it's an unconstrained sum. And because it's an unconstrained sum, and the function f that we are using, that itself factorizes, what that means then is that the grand partition function itself completely factorizes. And that's the reason why we do it. And then it's very easy because it factorizes into what I've shown you on the second line here, the product over states. And then all I have to do is do the calculation for each state. And for each state, n is just 0 or 1. So there's two terms. One, when n is 0, you get 1, and when n is non-zero, when n is 1, you get e to the minus beta. And so we just have the product of that. So why is that good? Well, because what we showed when we introduced the grand canonical distribution is that there's a thing called the grand potential, phi, and that thing is like the Helmholtz free energy for the Boltzmann distribution. So phi is equal to minus kBt times the logarithm of the grand partition function. And that, I showed you, was equal to minus PV. So what that means is then if I want to compute the equation of state, then PV over KBT is just the sum over states of the logarithm of 1 plus e to the minus beta epsilon minus mu. So in other words, when I take the logarithm, the product that we have over here, that product then becomes a sum of the logarithms over here, and we can do that sum by turning it into an integral, as we will see shortly. So that is why it's a very convenient way to get the equation of state. The only problem is that what we don't know is we don't know what mu is. And as I explained last time, we have the constraint equation. And that constraint equation determines n by saying take the derivative with respect to the fugacity lambda d by d lambda of log is then just the sum over I of what I've written down over here. And that thing over here, this is indeed just the Fermi-Dirac distribution for the expected occupation number of every single single particle quantum state. So I have two equations when I'm doing the grand canonical distribution. One is the equation of state, the other is the constraint equation. You have to solve both of those simultaneously in order to be able to solve the problem. Now, when you've got individual non-interacting particles, it's not too bad to be able to do that. When you have a system which is actually interacting, a many-body system, then it becomes very complicated. So now let's wrap up. So I've now told you two things. One is why the grand canonical distribution is a good thing. The reason it's a good thing is it makes the algebra simple. Okay. The second reason is that it makes physical sense. As I've emphasized many times, what you're doing with the grand canonical distribution is taking an isolated system at energy E, as shown at the bottom, and then we're agreeing that inside the blue lines, that is the subsystem where we are interested in, and particles are flying into and out of that, carrying kinetic energy. And so the particle number is varying and the energy is varying. And we know that the condition for thermal equilibrium is that the chemical potential is a constant and the temperature is a constant. And then the average energy of that subsystem will be fluctuating as particles come in and out. But the whole overall system is isolated. And so that is the grand canonical distribution in a nutshell. Okay, so any questions about that before before we go on? Okay, I see no question. So I got 5 minutes left. Let me just very quickly finish up this calculation for the fermions. So what I want to do now is I want to write down the explicit calculation of the sum over states going into an integral over wave numbers or integral over momenta. So let me write it like this. What we're going to do is we're going to write these formal sums as an integral. And I'm going to do it like this, d3k. So what we're going to see then is that PV over KT is equal to V over 2 pi cubed. And that's our density of states in K space, the integral d3k, and then the logarithm of 1 plus the fugacity, E lambda, times the energy, which is e to the minus beta, h bar squared, k squared over 2m. So that is the integral that we have to do. And then we have to determine lambda, and lambda is determined by the fact that n is equal to v over 2 pi cubed times the integral d3k, and then we have to do the same thing for the Fermi-Dirac distribution. So we get 1 over lambda times e to the beta h bar squared k squared over 2n. So that's roughly speaking what the two equations are, written down as integrals. And now I'm going to do a little bit of cosmetic presentation on these things. So this is cosmetic things. So what I'm going to do is I'm simply going to say that we'll write P is equal to h bar k. So we'll write it down in momenta. I'm going to generalize to arbitrary spin. And when we have arbitrary spin, the degeneracy is 1 plus 2s. And so then I can write these equations down as the following. P over kbt is equal to 4 pi times 1 plus 2s over h cubed. And then the integral from naught to infinity, p squared dp times the logarithm of 1 plus lambda e to the minus beta p squared over 2m. So that's the equation of state. The volume factors have cancelled. And then for the constraint equation, I'm going to write that as n over v is 4 pi over h cubed times 1 plus 2s, the integral from naught to infinity, p squared dp, and then 1 over 1 plus lambda to the minus 1, e to the beta, p squared over 2m. And so those are the two equations that have to be satisfied. And so you can think of it like this. Look at the bottom equation, the constraint equation. I know what n is, I know what v is. So then I find, and then I know what beta is, which is kt, 1 over kt. So I do the integral over momenta, and I find what value of lambda enables the integral on the right-hand side to equal the number on the left-hand side. So now I found lambda. Then I plug that value of lambda at that value of temperature into the top equation, and then do that integral, and thus work out the equation of state. So let me just, of course, in practice, you have to do this numerically. So let me tell you some mathematical expansions that you can use to approximate this. So this is nothing fundamental, but just some expansions for these integrals. So we can do we can write in this way. I'm going to define two functions. So one function I'll call f 5/2 of its argument z, and that function is defined to be this: 4 over the square root of pi times the integral from naught to infinity dx x squared, the logarithm of 1 plus z e to the minus x squared. So that's how I'm defining this function. So just to make sure you understand, here is the variable, z. You tell me what z is. That number z appears here. Okay, it's basically something like the fugacity. Okay, so that's what that is. X is just a dummy variable which you integrate over. It's just the momentum. So that's this function f 5/2, and then there's another function which I'll call f 3/2 of z, and that one is defined to be z df of 5/2 by dz. Okay, and those are these two functions. Now, this the reason we write it this way, now we've just got a function that has to be evaluated, and we can make an approximation for these functions. So one obvious way that you might do it is you might say, well, we can make a power law expansion in Z. So let's see what that looks like. So if I do that, then F5 halves of Z is equal to this power series, the sum from n equals 1 to infinity of -1 to the n plus 1 times Z to the n over n to the 5 halves, and F3 of Z, F3 halves of Z, I should say, is equal to the sum from n is equal to 1 to infinity -1 to the n plus 1, Z to the n over n to the 3 halves. And so why these things are interesting, okay, there's no real physics to this, but this is interesting because these functions, you might see, they are generalizations of something called the Riemann zeta function. So there's interesting connections between statistical mechanics and pure mathematics, things like the Riemann zeta function. Okay, so let me then tell you some approximations, and then we will finish from this. So there's some approximate results. So the advantage of doing a power series expansion is you can just expand things, like the power series expansion for hyperbolic tangent or something like this, right? So let me tell you what are these expansions, and I'm going to show you for F3 halves. So it can be shown, and you don't need to know how to prove this. F3 halves goes like this. It goes as Z minus Z squared over 2 to the 3 halves plus Z cubed over 3 to the 3 halves minus Z to the 4th over 4 to the 3 halves, and so on and so forth. And that's an expansion that's useful when the argument Z is much less than 1. And then when Z is large, F3 halves has a different expansion. It looks like this: 4 over 3 root pi times the logarithm of Z raised to the power 3 halves plus pi squared over 8 times the logarithm of Z to the -1/2 plus higher order terms. And those terms, I think, go like order 1 over Z. And so this is, sorry, there's extra terms that go like 1 over Z. And so this is true when Z is much larger than 1. And so these functions can be approximated, and like a lot of things in statistical mechanics, once you've done the physics, there's a lot of sort of mathematical analysis that can be done. Let me finish by showing you what this function looks like, and then I'll tell you why it is interesting. So this is Z, this is F3 halves, and this is a function that grows like this. So it starts off linearly and it goes up like this, and then eventually it does something like that. So what's happening here at the origin, so here it is going something like order Z, and then somewhere up here for large values of Z, it's going as 4 over 3 root pi times the logarithm of Z to the 3 halves. And so one understands a reasonable amount about the mathematics of this. Now, why is it interesting? So who cares? So what we're going to finish with is question, why is this useful? And the answer is that we can compute the first quantum corrections . to classical equation of state. And we're going to see a result that is really, really quite beautiful. So what I'm going to do now is I'm going to go back and take the constraint equation, and I'm going to do this. We're going to write the constraint equation as this. Remember, we talked about this quantity called the thermal de Broglie wavelength. So that thermal de Broglie wavelength times V over 1 plus 2s is equal to f3/2 of lambda. Okay, so just a quick recap. So V is 1 over n, which is the volume per particle. 1 plus 2s is the degeneracy factor, and then this lambda is e to the beta times the chemical potential. Okay, so that is that is what the constraint equation is. Now, let's remember what our interpretation is of quantum mechanics. So we know that when lambda t cubed over the volume per particle is much less than 1, that is a pure number. It's a volume, a length cubed divided by a volume per particle, so it's a volume. That says that the interparticle spacing is much greater than the thermal de Broglie wavelength. And that limit then is the limit where the particles are not seeing each other's quantum mechanical wave function cloud. They're so far apart, they never realize that there's a wave function around the atoms. And so this limit is the limit where you see classical behavior. And you can see that this function f3/2 is linear near the origin. So that linear near the origin, when you're saying that z is going as lambda, that is the case then where lambda cubed over v over times the degeneracy factor is actually very small. So what that means is that the behavior of f3/2 of lambda being nearly linear near the origin is equivalent to the classical limit. So that's the so what I've just told you, what I've just shown you then, is that this behavior here is the classical case, and this behavior up here is the quantum case. Okay, so let's just check if that is actually true. Therefore let's expand the function f3/2 of lambda. So that goes like this: lambda t cubed over v 1 plus 2s. So that is going to equal lambda minus lambda squared over 2 to the 3/2 plus some higher order terms. And then if I make lambda the subject of that equation, and that implies that lambda is equal to lambda t cubed over v 1 plus 2s. And then the next term is 1 over 2 to the 3/2 lambda t cubed over v 1 plus 2s, and that whole thing raised to the square power plus that thing terms of order, that thing raised to the cubic power. So how did I get this? Well, one way to do it is you can say, let's just take this equation up here. Let's just take it to second order in lambda. Then solve it as a quadratic equation, and then expand this square root, and then I would get the result that I've got down there. I did it a much quicker way in my head, and you could do it like that too, because here's how I did it. What I said was, we know that the first thing you can say is that the lowest order approximation is that this thing is equal to this. So what I did was I just solved this recursively by saying lambda is equal to lambda cubed over v1 plus 2s plus lambda squared over 2 to the 3 halves plus dot, dot, dot. So that's a true statement by making lambda the subject. And then I say, then I first of all iterate this. So step one is I just do this. That gives me lambda. That gives me lambda. Then step two, substitute that 0th order approximation into the right-hand side. So that value then goes into, so this is lambda 0, then I add that into here, and then that's how I got this result here. So this is a much quicker way than solving a messy quadratic equation and then expanding the square root. I solved a nonlinear algebraic equation by a recursive iterative way. So this is a nice trick, a nice recursive iterative way to solve a nonlinear equation, algebraic equation. Okay, so now let's put this value. Now that I know lambda, I can now put this in to the equation for P. So now then we can say then that P V over KBT is equal to V1 plus 2S over lambda cubed, then times lambda minus lambda squared over 2 to the 3 halves. And if I do that, I get 1 plus lambda t cubed over 2 to the 3 halves, 1 plus 2s times little v plus dot, dot, dot. So I'm nearly finished. Okay, so just hang on for 1 second, okay? So what does this tell you? So the first term, PV over KBT is equal to 1. That's the same thing as PV equals N KBT. That's the classical equation of state. Okay, so that's what that is. The second term, this term here, second term, is the lowest quantum correction. Due to Fermi statistics. And look, it increases the pressure. Why do you think it does that? Why does the lowest quantum correction to classical behavior increase the pressure for a Fermi gas? Well, it's not just degeneracy. What's the physical reason? Exclusion, right? The fermions don't like to be in the same state. So it's like what you were saying, degeneracy, but they don't like to be in the same state. So if you try to put them into the same state, they push away from that. Okay, they want to go to a higher energy state. So now we have an actual force, because pressure is just force, an actual force due to quantum statistics. And what do you think happens for bosons? So what's the quantum correction? Well, there is a limit where bosons behave like ideal gases, right? So we're looking at the first. We're not looking at low temperatures. We're looking at the first correction as you lower the temperature from infinity. The first correction to the equation of state due to the emerging presence of quantum mechanics. So what's going to be the sign of it for if the sign of it for fermions is positive, what is the sign of it for bosons? Negative, right? Obvious, okay, right? So I'm asking that because it can only be one or the other, right? So the bosons, they love to be in the same state. That's Bose-Einstein condensation, which we will talk about next time. So now you see that actual quantum statistics. So this is an actual force due to quantum statistics, in particular the Pauli exclusion principle. And this is a force. This is as you go, you see this as you go down from very high temperatures. You see the first evidence of quantum mechanics. Okay, and as you said, for bosons, it's negative. So in the next homework, you'll get an exercise where you'll just do the same calculation that I just did for you, but you'll do it for bosons, and you'll see how you get that. Okay, so that's enough for today. So we will end there. Let me just stop the recording, and